These are the notes for Algebra 2, Section 7.6, the second part of the notes for 7.6. This time we're dealing with logarithmic equations. We're solving logarithmic equations. I've split this up into two parts. So we're looking at the first part today. Now, solving logarithmic equations is a lot like solving exponential equations. Or a logarithmic equation, of course, involves logarithms of variable expressions. So if I had, for instance, log base 2 of x equals 15, that would be a logarithmic equation, and I could use these techniques to solve it. The biggest trick that we're going to see here will be using the property of equality for logarithmic equations, right? We can solve most logarithmic equations using that. And we've seen the property of equality for exponential equations, and it's, of course, very similar. If b, x, and y are all positive numbers and b isn't 1, then log base b of x equals log base b of y if and only if x equals y. This is very similar to the property of equalities for exponential equations. Remember, the exponential equation says that if I have b to the x equals b to the y, then x equals y. This is basically the same thing. If I have log of x equals log of y, then x equals y. So, for instance, as an example, if we had the log of 3, or log base 3 of x equals log base 3 of y, then x equals y, right? These things can go away. And just like with exponentials, that's a handy little trick. That'll make life a little bit easier for us. So let's look at a couple of examples here. Our first example, we have log base 7 of 6x minus 16 equals log base 7 of x minus 1. So that's what we're starting out with. Now, of course, immediately we should see that we have log base 7 here and log base 7 there. And if they're both log base 7, and that's all I've got, well then, according to that property of equality, 6x minus 16 must equal x minus 1. And, of course, that is an equation that we can solve straight up. We can start by subtracting x from each side so that we can get all of the x's together, leaving us with negative 1 on one side and 5x on the other, minus 16 on the other. Then we can add 16 to both sides, right? So we add 16 to both sides. That would be a good next step. So plus 16 here, plus 16 there, trying to isolate the x. We get 5x equals 15. Negative 1 plus 16 is 15. Then, of course, we can divide each side by 5. Divide by 5, divide by 5, and, of course, x equals 3. La-di-da, there you go. So, of course, most of this is just standard, boring old solving equation. The only trick was, I had log base 7 here, and I had log base 7 there. Big whoop, they went away. One thing that we are going to want to do is check to make sure that these actually work. Now, the trouble with the logarithmic equations is that the domain of logarithmic functions is restricted, right? Those were the weird ones that we graphed, and they had the vertical asymptote. So we had a restricted domain. So we need to check to make sure that the solution that we got, 3, right, x equals 3, actually works in our equation. So we're going to substitute x equals 3 into the original. All right, let's do that. We'll have 6 times 3 minus 16 equals 3 minus 1. Right? Log base 7 of 6 times 3 minus 16 equals log base 7 of 3 minus 1. Well, 6 times 3, well, that's 18. 18 minus 16 is 2. So we have log base 7 of 2 on one side. On the other side, 3 minus 1 is 2. So we have log base 7 of 2, and the solution checks, right? It works. Log base 7 of 2 does equal log base 7 of 2. Let's try a different equation. We're going to use a slightly different technique here. As you know, sometimes when we have an exponential equation, we can solve it by taking the logarithm of both sides, right? We take the log of both sides. Well, the reverse works with logarithmic equations. If I have a logarithmic equation, sometimes I can solve that by exponentiating each side. Now, exponentiating is a really big word that basically means take whatever you've got and turn it into an exponent. So we're going to have exponents. Now, to exponentiate these sides, we are going to want to turn them into exponents with a base that is the same as the log's base. So in this case, this is log base 5. So we want to turn it into an exponent with a base of 5. So let's do that. We're going to have 5 to the log base 5 of 3x minus 8. Right? This is one of those times when you might want to write really big so that it's easy to write this down and not make any mistakes there. On the other side, 2 is also going to become an exponent of 5. So we're going to have 5 to the second power. Now notice our original equation is still there. Log base 5 of 3x minus 8 equals 2. But now, both of those sides are exponents. And we are allowed to do this. I know it looks a little weird, and you go, whoa, what's that about? But if you'll notice, this looks exactly like the exponential equations that we were solving, where if we had the same base on both sides, they canceled out and we were just left with the exponents. Well, this is exactly the same thing. We're just working the opposite direction. So it still follows. It still works logically. Now, of course, I have 5 to the log base 5, and that cancels out, leaving us with just 3x minus 8. All right, because b to the log base b of x just equals x. On the other side, 5 squared, well, that's 25. And from here, two-step equation. We're just going to solve boring old standard two-step equation. We'll start by adding 8 to each side. Gives us 3x equals 33. 25 plus 8 is 33. Then, of course, we will divide each side by 3. And x equals 11. So our solution is 11. We still have to check that because we still have to make sure that it actually works. So let's do that. Let's check. We're saying that x equals 11. So let's check to make sure that x equals 11. Oops. Make that equal 11. So, we'll plug it in, see what happens. We'll have 3 times 11 minus 8. Well, that equals 3 times 11, of course, is 33. 33 minus 8 is 25. Now, because 5 squared equals 25, log base 5 of 25 equals 2. All right. That's not unusual. That's the evaluation process that we went through before. Now, as you remember, the evaluation process for logarithms says, what power do I raise 5 to get 25? And the answer to that is 2. I raise 5 to the second power to get 25. So, log base 5 of 25 equals 2.